Everyone looking at class number 24, our goal is to use free body diagrams to solve for the acceleration of an object. So we've actually done stuff like this before, but we've never drawn free body diagrams. So we're going to do now as if we don't know what free body diagrams are, and then we'll see how to draw them appropriately. So the first one says a net force of 3 newtons is acting on a 454-gram object. What is the acceleration of the object? Be careful for the units of mass here. So whenever we do any question this year, you really have to make sure that the units for mass are in kilograms. So if we have 454 grams, we want it in kilograms. So always multiply by what you want over what you have. And we know that there are 1,000 grams in 1 kilogram. So we get 0.454 kilograms. So that's our mass. All right. Now for the next part here, we know that the net force, F net, is equal to 3 newtons. Now that's not just one of the forces. There could be 5 forces acting on this thing, but at the end of the day, they all add up, subtract, cancel out, and we are left with 3 newtons of force. And we're looking for the acceleration. So A equals F net over m. And we have 3 newtons over 0.454 kilograms. And we're left with 6.6 meters per second squared. A newton divided by a kilogram is a meter per second squared. Now the next one says a force of 40 newtons pushes a 5 kilogram box forward on a rough surface with an acceleration of 2 meters per second squared. What is the force of friction acting on the box? Do not assume that this 40 Newton force is the net force, especially because it mentions that there is another force here, which we don't know, and what we're looking for, the force of friction. So let's just write down some givens for now. Just hold off on writing down the force. So the mass is equal to 5 kilograms, and the acceleration is equal to 2 meters per second squared. So you can actually find the net force, okay? You can't find each individual force, but you can find the net force right away. A equals F net over m. Again, the net force being the total of all the forces added together. 2 meters per second squared divided by net force divided by the mass, which is 5 kilograms. All right, so we're going to cross multiply here. So 5 times 2 is going to be 10. So our net force, F net, equals 10 newtons. That means that the total, the sum of all the forces put together is 10. Okay, so think about that. If we have 40 newtons pushing forward, but we need a total of 10 newtons, what does the frictional force have to be to get us to 10? Now, most of you might think, oh, it's negative 30. And you'd be right in saying that. But how could we do this from a more mathematical standpoint? You could say that F net equals the sum of forces, sum of all the forces. So you could say that F net, which is 10, is equal to, well, the sum of all the forces would be 40 plus the frictional force, which we don't know. And you would find that the frictional force is equal to negative 30 newtons. So you could either kind of just think about it and think that it's like figure out that it's 30, or you could set it up like this mathematically and make a little algebra equation. Some people find this method to be much more challenging, but that is the more correct way to do it. So let's talk about free body diagrams. What are they? Basically, it's a way to keep track of our forces. You'll notice here that like it could become a little bit confusing. Like, okay, there's a 40 Newton force, there's a force of friction, the net force is 10. It could definitely be confusing. A free body diagram is just a way to keep track of all your forces. All right. So what does a free body diagram look like? Basically, it just has all the forces acting on the object, and we represent each of those forces with an arrow. The arrow represents the strength of the force and the direction of the force. All right. So for example, in the case of an airplane has 4 forces, 4 main forces acting on it. We have lift. That's what keeps the airplane up. We have weight, okay, which pulls everything down. You could also call this the force of gravity, okay, which I will some of these. We have thrust, and we have drag. Drag is also like air resistance. Now, every free body diagram is going to be different. In this case, the airplane has these 4 forces acting on it. In a different case, it might have none of these 4 forces acting on it. But in this scenario, those are the forces acting on it. So we're going to draw 4 free body diagrams right now. We are not going to include air resistance or drag on any of them. So as we said in class, we are always going to represent objects as a dot. Don't actually draw the book. Don't actually draw the wrench. Don't actually draw the car. And don't actually draw the ball, though a dot does kind of look like a ball. The reason being, I just don't want you getting caught up with, pictures, and it could actually make the free body diagram harder to read. So a book sitting on a desk, let's start with that one. So a book sitting on a desk, of course, it has gravity acting on it downward. You could call that weight, or you could just call it gravity. Now, gravity's pulling it down, so why doesn't the book just fall? Well, because there is a force of the desk pushing it up. Okay, so force of desk. Now, this force acts on anything sitting on a surface. For example, you're sitting in a chair right now. You feel the chair pushing up on you. Okay, if you like wiggle around a little bit, you'll feel it for sure. So the chair is pushing up on you. That's what prevents you from hitting the floor. Go to the wrench next. So the wrench, of course, has gravity acting on it. I shouldn't really be writing gravity. It's really the force of gravity or weight. Okay, now what is holding the wrench up? Well, some people might say, oh, it's your hand pulling up on it, but no, look at the wrench. What is actually keeping the wrench up? That force would actually be the string. Now, some people might call that tension, but for now, we'll just call it the force of the string. All right, let's go over here to the car. So car on the road, so gravity's, again, pulling it down. You could also call that weight, doesn't really matter. Let's see, so gravity's pulling the car down. If the car were on a bridge, let's say, why doesn't the car just fall into the water? Well, because we know that the road is keeping it up. Now, some people are saying thrust propels a car forward. That's actually not what propels a car forward. Okay. It's a little bit tricky to think about, but put it this way. If a car were on ice, or if you were trying to walk on ice, why is it so hard to walk forward or drive forward in the car? Because there's a lack of friction. So, though friction generally opposes motion, in the case of wheels on a road, friction actually propels the car forward. You can think about the tire as it hits the road and the tires are spinning. The tires are literally pushing off of the road and pushing the car forward. So as the tires push the road back or try to push the road pushes the car forward. Okay, that's actually a really good example of Newton's third law. Equal and opposite forces acting on two different objects. The car tire pushes backward on the road, therefore the road pushes forward on the car, propelling it forward. Okay, if the car were skidding though, friction would actually be slowing it down. Okay, or if the car were trying to stop, friction would be slowing it down. All right, so a ball falling. So a ball is falling again, there's no air resistance, so it's falling. So we know gravity is pulling it down. And a lot of people in class are saying, oh, lift is what keeps, there's a force acting upward on it. No, lift is pretty unique to aircraft. So there's actually no upward force acting on it. Because if I were to ask you the question, what stops the ball from falling? Nothing, it's falling. So there is no upward force acting on it. So it's just gravity. When any object is only under the influence of gravity, we call this free fall. When only under the influence of gravity. All right, so here's a step-by-step process for doing free body diagrams. It looks really extensive, but it's actually quite simple. So number 3 says in a frictionless vacuum. So just so you know, in a frictionless vacuum, that means no friction. Obviously, that's what frictionless means. And a vacuum means no air. Two men are pushing on a block from opposite sides. The block has a mass of 15 kilograms. I'll just jot that down for now. All right. Let's see. Man A pushes the block to the right with a force of 16 newtons. Man B pushes the block to the left with a force of 18 newtons. What is the magnitude of the block's acceleration? So when I say magnitude, I mean I don't care positive or negative. Just give me the number. All right. So for starters, you always represent objects with a dot. So that's step 1. That one step of the 5 is already done. Draw a dot. Now draw and label arrows to represent the forces acting on the object. The directions of the arrows matter, so don't just draw them in any which direction. The tail of the arrow always starts at the dot and points away from it. And each label should include the magnitude of the force, meaning the number, and the direction, positive or negative. If you don't know the value, just write down its name. But in this case, we're fortunate we know the values. So man A pushes to the right. Just take a sec. Why is this wrong to draw? The man is pushing to the right. Well, it doesn't matter if he's pushing or pulling it. Arrows always start at the object and point away. So the man who's pushing it to the right, his arrow is going to point starting from the object and going to the right. We'll call to the right positive. Man B is pushing to the left. We'll call it negative because it's to the left. Now we have 2 more forces here. We have the floor pushing up on it, and we have gravity pulling down. Now we'll talk more about this at a later time, but gravity and the floor, those forces, the floor pushing up on the box and gravity pulling down, they actually cancel each other out perfectly. They're equal and they are opposite. Cancel. Okay. So we're only really left with 2 forces. Okay. We're already on step 3. Look at that. Already on step 3. Right? Our only equation right now, A equals F net over M. That's it. That's the only equation. Now, this next part is a part that a lot of people really struggle with, but all I want to emphasize is that it's actually a very simple step, but a lot of people just don't realize they have to do it. Okay. You are going to replace F net, this right here, with all the forces on your free body diagram. So you're going to take these forces, this one here and this one here, and you are going to plug them right into F net. Just put them right in. A lot of students struggle with that step. Don't struggle with it. Just realize that when I have F net, I have my free body diagram, just take those forces and plug them right in. So A is our unknown. F net is negative 18 plus 16. Now you could just skip a step and say negative 2, but get in this habit for now. Divided by, we already know the mass is 15 kilograms. And we get negative 0.13 repeating meters per second squared. That negative means left. All right, so it asks for the magnitude, so I can just write the number 0.13 meters per second squared. All right, now a lot of you might be saying to yourselves, well, I could have done this way quicker. I could have said, I know, 16 to the right, 18 to the left, so I'm left with 2. 2 divided by 15.13, done. And while that works, it's good to use a simple example like this to show the proper method for doing a free body diagram. All right, let's check out another one here. Repeat step 3, but now both men are pushing in the same direction. So first step, draw a dot. Second step, draw all the forces acting on the object. So we have 16 still, and we're going to say they're going in the same direction. Some people put them tip to tail like this and drew the 18 like that. While that's not entirely wrong, it is a good habit, though, to get in that they are starting at the dot and pointing away. Okay, so that's 18 newtons. All right. So 2 steps down. Third step, A equals F net over M. Fourth step, plug in these 2 forces into F net. Put them right in. Just throw them right in. Okay, so I have A equals 16 plus 18 divided by 15. And I get an acceleration equal to, I think, 2.27 meters per second squared. All right, there you go. Now, the reason it asks for magnitude is because, like, let's say you decided to make left the direction they were both pushing. You're allowed to do that. It didn't really say, just said put them in the same direction. So, you could have done it either way and gotten 2.27. So here's a question from last class, and we can use free body diagrams to help us here. Though you don't absolutely need to, you can. So the first thing says, calculate the magnitude of the net force acting on the box. All right, so for starters, well, we know there's a 15 Newton force pulling forward. That is not the net force, though, because it's implied that there is friction, a rough surface. Also, there's another force because it asks you for the force of friction in the second part. So we know the mass, 2.5 kilograms, and we know the acceleration of 2 meters per second squared. Therefore, we know the net force, A equals F net over M. This is very similar to what we did last class. F net is equal to 5 newtons. All right, so that's the first part, 5 newtons. Now determine the magnitude of the force of friction acting on the box. Again, you know that F net is equal to 5. You know that there is 15 pulling forward, so how much has to be pulling back to give you a total of 5? You could say 10. But draw the diagram. It's useful. So we know that there are 15 newtons going forward, and we know that there is a force going back. We don't know it. We know that the floor is pushing up, and we know that gravity is pulling down. As we've discussed, gravity and the floor cancel out because they are equal forces in opposite directions. So those cancel. Okay. Now, coming back here, we know that these 2 forces together add up to be F net. So I'm not even going to write A equals F net over M. I'm just going to say that F net is equal to 5 because we already found that out. And then I simply want you to take these 2 forces in orange. Take this force, plug it in here, and this force simultaneously plug it in there. And we get 15 newtons plus the force of friction equals 5 newtons. Now you might be saying, do I make the force of friction negative there? Well, you might not know it's negative. Okay. I mean, I know we know friction opposes motion, but if it were a different force, you might not actually know that it's negative. So it's good to actually do the math and get a negative number. In this case, then we would get the force of friction is equal to negative 10 newtons, meaning that friction points left. Okay. They didn't ask for the magnitude, so they'll just look at the number. Whether you write 10 or negative 10 is fine. All right. So get in the habit of drawing free body diagrams for any force question. They'll help you out a lot in the long run.